Good morning, everyone. It's always a pleasure to come up to Santa Barbara. I tried to choose a color scheme that was appropriate for the venue and for the topic at hand, which is, as the close-in part of the planetary systems, which is super exciting. So I'm Jessie Christiansen. I'm the chief scientist of the NASA Exoplanet Science Institute at Caltech IPAC. Just a 15 seconds. IPAC is a science and data center on the Caltech campus that runs a bunch of NASA and NSF archives and projects and mission operations. So in case you don't know what IPAC is, we're at Caltech. We did, for instance, Spitzer was run by IPAC. So let's move forward. Okay, so an overview of what we'll cover this morning. It's early in the morning, but let's get straight into it. Why do we care about the very inner part of the inner disk, as Eric introduced? I'm going to go through a bunch of observations that have been made. I'm an observer. I'm not a theorist. And a lot of the people who will follow me will help explain why we see what we see. But I'm going to start by saying I don't have any answers for you guys this morning. And that would be a really boring first talk of a conference if I came out and I was like, we've solved it all, here are all the answers. What I have are a bunch of questions. I have a bunch of observations that we don't understand yet. And that's the point of a conference like this and a long stay like this at KITP. Why do we see the things that we see? What's causing these distributions that we're seeing at these snapshots in time? Okay. So why do we care about short period planets? This is a plot showing, this is orbital period, sorry, the footer is on top of it, on the x-axis, and planet mass, or m sin I, on the y-axis. Where we don't have a planet mass measured from the actual technique, we've used a mass-radius relation to map a transit radius onto a mass. So this is the distribution of planets as of, what is the date? As of 4 days ago on the NASA Exoplanet Archive. Now, part of the reason we care about short-period planets is because of observational biases, right? The techniques that have been most successful at finding planets so far, which are transits and radial velocity, these top two, are biased towards short-period planets. Now, this very inner region, I'm going to point you at Eve's talk on Wednesday to talk about what's going on further in here. But the first thing I'm going to point out is, we have this wall here between 1 and 10 days that we're going to talk a little bit more about. But this huge pileup of planets is an opportunity, right? This is biased. We know we're not seeing all the planets that are out there. We're seeing a biased view of planetary systems because of our techniques. But we have all of this data. So we can start asking questions, and that's why it's interesting. So this is now just a histogram of the number of planets we have with period, and this is a little unfair, so I'll put it in log space. But it is to say that almost all of the planets we have are at very short periods. 4 out of 5 planets that we know of today have periods closer than 100 days, and nearly half of the planets we know have periods closer than 10 days. So this, again, really exciting opportunity. Mercury is the only one that we have in this region, and I'll point you at Matt's talk on Wednesday to learn more about why Mercury is interesting. Okay, we're blitzing right through it. Okay, so why do we care about these planets? So this is an animation that we're going to come back to later in the talk. This is a 12-day orbital period. This is a star. And this is an animation of all of the different processes, many of the different processes that are happening very close to the star. And it's almost everything we care about with planets. It's planet formation, it's planet migration, it's planet evolution. All of these processes that we care about and we're trying to understand the underlying physics of happen close to the star. So even though we're biased and we only have this sample that is very close to the star, we can still learn a lot about all of these interesting planetary processes: formation, migration, evolution. So we're going to come back to that one later in the talk. Okay, where did my title go? Here we go. All right, so coming back to this plot, the first thing we're going to talk about is the orbital distribution of planets close into stars. Now, again, this is just a superset of all the planets that we found, right, from many, many, many different techniques. So no one should ever do statistics on the NASA Exoplanet Archive. Let's say that, and I'm going to stare at everyone in the eyes. Never do statistics on the NASA Exoplanet Archive. I love it dearly. It's a superset of many, many different surveys and many, many different observational biases. But there are things you can say broad strokes. And one of the things you can say is that for giant planets, so this is mass again, so let's look above 10 to the minus 1. For giant planets, there are more cool giants than hot giants. These are easier to find. These are harder to find, and we see many more of these, so that means intrinsically these are more common than these. But you can see this interesting feature here, and it's a pile-up of giant planets at 3 days. Right, so this is a histogram again with period, now pretty close in. And there's a pile-up of hot Jupiters, so planets above about 8 times the radius of Earth, so Saturn's up, at 3 days. Now, this is one of the earliest features that we see. Hot Jupiters were the first kind of planet we found around sun-like stars. They're really interesting. They're actually intrinsically rare, but they're really interesting and they tell us interesting things. So this feature, this pile-up at 3 days, this is a 30-year-old observation at this point that hot Jupiters do this. And we're still trying to really, really nail down the answer. So I went through a bunch of papers last week to try and see if we had the answer yet. I don't think we truly have a everyone agrees answer. There's a lot of different processes. So let's talk through some of them. This is a cartoon. This is a cartoon. She says confidently. This is a cartoon from a paper by René Heller, who I emailed to say, is this cartoon correct? And he was like, yes. So good. Thank you. Okay, so this is a protoplanetary disk at 1 million years old, orbiting a very fast rotating star. When stars are young, they're rotating very quickly. Thank you, Eric. And this is a giant planet, a seed of a giant planet. Now, when it forms, what it feels when the protoplanetary disk is there is a protoplanetary disk torque, which is pushing it in towards the star. So we're going to watch this get older. So that's the net torque on this planet at the moment is inward migration. Once we get to 10 million years, the protoplanetary disk is going away. Right? It doesn't last very long, a few million years. By the time you get to 10 million years, it's going away. The star is slowing down as it ages. This co-rotation radius is moving in. And what you feel now is net zero torque at this point. So you have the protoplanetary disk torque pushing in, but you also have tidal dissipation from the star, because now you're close to the star, which is spinning, which is pushing you out. And at some point, you balance. You stop migrating in, because the force pushing out is equal to the force pushing in. I say it like this because I'm not a theorist. I'm using the 5th grade level words, because this is my level of understanding of how this works. So you have net torque here, and so you stop moving in, and then we keep going. So after 100 million years, the disk is gone, the star has slowed down. The co-rotation axis for a sun-like star is about 0.02 AU, and the net feeling that we have now is this tidal dissipation, which pushes the planets out, and then they all end up at about here, which has to do with the rotation of a sun-like star at 100 million years. So this is one possible sequence of events that captures a bunch of the different processes that are happening. This is just migration through a disk. There's a whole other avenue, which is planets interacting with other planets, that some planets push out, some planets push in as they exchange energy and momentum, which can also drive planets in. But the question is, why do we get this pile-up at 0.05 AU? And one possible answer is that it has to do with the tidal dissipation of a star rotating as a sun-like star does at 100 million years. So, one possible set of answers for a pile-up of hot Jupiters. But I wanted to use this one as an example because it captures both the number of different types of processes that can be happening. You've got lots of different things going lots of different directions as age is changing. And also the uncertainty, right? Like we don't know all of the details of this process, and we don't know if this is truly the explanation for the pile-up at 0.05, but it is an overall picture that captures a bunch of processes. So there's a pile-up at 3 days for giant planets, which is one of the things that this conference should hopefully, again, I'm not giving you answers, I'm giving you questions. Why is there a pile-up at 5 days, at 3 days? Okay, so now let's go to smaller planets. This is the period distribution from Eric Pettigrews' paper from a few years ago of purple is sub-Neptunes, so between 2 and 4 times the radius of Earth, and orange is super Earth, so between 1 and 2 times the size of the Earth. And what you see is that they also have a peak. It's not as dramatic a pile-up, right? So that's already a clue. It's a very different shape to the hot Jupiter pile-up. They do have a peak, but it's further out. It's further out than the hot Jupiter peak. The hot Jupiter peak was here at 3 days, and what we're seeing for these smaller planets is a peak at more like 10 to 20 days. So whatever's happening to the hot Jupiters is happening differently or at a different amount than is happening to the smaller planets, because we see a peak, but it's nowhere near as dramatic. And so there are a lot more slides I can add here, but there's a lot more part of the talk I want to get to as well. The location of the pileup, which depends on this physics, right, the underlying physics of what's happening, does seem to have a dependence on planet mass. This is what we showed with Jupiters and super Earths and sub-Neptunes. It does seem to depend on the stellar mass. The size of the star determines where this pileup is. It does seem to depend on stellar metallicity. How many heavy materials are in the star seems to influence where this pileup is. I feel like we haven't even explored all of the ways that this depends on the birth environment of the planet. So there's a bunch of different ways that change where the pileup is, and we are still investigating fun answers, and I'm hoping to hear fun answers this week to why the pileup is where it is. Okay, so that's the orbital period distribution of planets. Let's talk about the size distribution of planets. One of the most interesting results that came out of Kepler was that small planets on short periods are bimodally distributed in size. There's not a smooth function, there's two peaks, right? There's a super Earth peak, which we just talked about, between 1 and 2 AU, and there's a sub-Neptune peak between 2 and 4 AU. 1 and 2 Earth radii and 2 and 4 Earth radii. So we see this two peaks. So that means physics is happening, right? Something is happening to carve out this two peaks, and that's interesting. So this is a result from Kevin Hardigree-Ullman from a few years ago, showing that if you looked in the K2 data, so after Kepler wasn't able to look at its original field of view, K2 went and did an ecliptic plane survey. If you look at the K2 data, which is a completely different patch of sky, you see the same thing. So this bimodality was not some quirk of the Kepler data, it was a ubiquitous feature across the sky. Small planets are bimodally distributed in size. And so these are short periods, these are all less than 80 days. And I'll show on another slide that this happens very, very close to the star. One thing I'm not going to talk about in detail, but I want to highlight right here is the idea of super puffs. So another size distribution thing is this idea that very, very, very close in planets are bigger than we think they should be in terms of their radius for a given mass. And so there's a whole population out here which are close to their stars and are puffy, and we don't understand them yet. So just keep that in mind as well when we're talking about size distributions. Anyway, bimodal distribution. And then a few years after this, the Kepler result came out, and then the K2 result, this really interesting result from Raphael Luc and Henri Paet came out, showing that for M dwarfs, specifically small cool red stars, if you very well measured the mass of the planet, this is all radii, right? This is a size and radius distribution. If you measured the mass as well, if you have radius and mass, you have density, right? So these are density contours here now. So this is the radius of the planet, the mass of the planet, and we have two density contours. One is an Earth-like density, so iron and silicon, and then the blue one is if you take that Earth-like composition and chuck half of it away and make half of it water, so a water-rich kind of world. And what they were suggesting is that it's not necessarily a radius bimodality, but a composition bimodality, that you have rocky planets and water worlds. That's your bifurcation is not in radius necessarily, but in actually the underlying structure of two different types of worlds. Now, this has not yet stood up for solar-type stars, for FGK stars. We haven't seen the same kind of clarity of bifurcation into these two densities contours for solar-type stars as we have for M dwarfs. But this is really interesting. Like, what is the underlying cause of this bimodality? So let's get into that a little bit more. So this is a plot from Van Allen from a few years ago. The gray points are the original Kepler data, and then the purple points are stars for which astroseismology, using the Kepler time series, has been able to really nail down the stellar parameters, which lets you really nail down the planet parameters. For a lot of these gray points, that error bars are driven by our uncertainty on the stellar size, which translates directly into uncertainty on the planet radius. So the purple points are the ones where we know very, very well what the star is, and therefore very, very well what size the planet is. And, you know, this cavity is so obvious, right? Like this valley here when you have the precise data. Now, I wanted to show this one to show that this does happen very, very close to the star, right? Like within 10 days, we see this gap. But I also wanted to show it because something that's really interesting that pops out of this is that the location of that valley between super Earths and sub-Neptunes changes as a function of period, right? The further out you go from the star, the smaller the radius at which that transition happens between the super-Earths and the sub-Neptunes. So that's a clue, right? Whatever process is doing this, whatever process is sculpting these two populations seems to have some dependence on the period of the planet. So let's talk through some of the leading theories as to what's creating this bifurcation. So I would say both of the leading theories in the literature, and there are more, I'm not going to talk about all of them, but these are the two that have gotten the most attention, are core-powered mass loss and photoevaporation. Now, both of these are mass loss mechanisms where a planet starts with a certain amount of mass and loses some through some process. Core-powered mass loss, it's the residual heat from formation of the planet that unbinds the upper atmosphere, blows it away basically, or untethers it enough that it can be removed by the stellar wind. And the other one is photoevaporation, where that young star and its very, very active stellar wind just blows away the upper atmosphere of the planet. Now, both of these predict that there's a critical mass above which you have enough gravity to hold onto your atmosphere, even in the face of the residual heat or the stellar wind, and below which you don't and you lose it, okay? And that this critical mass defines these two populations. That super-Earths, many of them may have started as sub-Neptunes and then lost their atmospheres and become super-Earths. So that valley is carved by these processes, moving a bunch of planets to smaller radii. Now, they both actually work with period because core-powered mass loss loosens the upper atmosphere enough that the stellar wind can take it away. So you still get this dependence on your nearness to the star, your closest to the star. And actually, it's very difficult to tell these two processes apart in the Kepler data because they both explain the Kepler data very well. But there is one place, at least, where they actually make quite different predictions, and that's the time scale over which they happen. So now the x-axis is age of the planetary system. Photoevaporation, again, because it's driven by the active stellar wind and the star and flares and energy, is predicted to happen most predominantly in the first 100 million years while the star is young. Core-powered mass loss is predicted to happen the whole time, but to be most efficient at unbinding the upper atmosphere between 0.5 gigayear and 2 gigayears. And for the details of that, I will point you at Hilke. Okay, so we do have different predictions about when these should happen, which means that we can ask the question, can we measure this? Can we map this out? So here are two data points that we had. This is the fraction of stars that have hot sub-Neptunes. So that second peak in the bimodal distribution, sub-Neptunes is the one we're talking about. They're bigger, we can see more of them. So this is how many young stars and then field stars have hot sub-Neptunes. Now, TESS is an all-sky survey that's looked at thousands of young stars. And so this is a data point from Rachel Fernandez from a couple of years ago now. And the error bars are huge. But this is consistent with every young star having a hot sub-Neptune, right? 1 on that y-axis means 100% of stars have a hot sub-Neptune. Now, when we look at 3 to 6 to 9 gigayear-old stars down here, it's much lower, right? It's like 20 to 25% of stars have a hot sub-Neptune, which is not negligible. We don't have a hot sub-Neptune, for instance, but 20 to 25% of stars. There is actually an error bar here. It's just inside the point because K2 is K2 looked at a lot more stars in this field. Okay, so something's happening to our hot sub-Neptunes between 100 million years and 5 gigayears, right? And this is consistent with mass loss. Now, if it's photoevaporation, what we expect is that this is happening very quickly, that we get down to this field level. If it's core-powered mass loss, what we're expecting is that it's taking a lot longer to come down to this level, right? So we have a hypothesis to test. Luckily, K2 looked at a couple of clusters, Pleiades and Praesepe and Hyades, which were 600 to 800 million years old. So the question is, where is that point? And it's still 100% of stars having a hot sub-Neptune out at 600 to 800 million years, if you look at the Praesepe and Hyades data. So if you take the current predictions of photoevaporation and core-powered mass loss at face value, either core-powered mass loss is driving this sub-Neptune loss, or photoevaporation takes a lot longer and acts a lot longer than we thought, right? Both of those can fit this. Now, this was great. This is a fun story, and I got to publish a paper, and it was lovely. And then this happened. So Rachel went back and took her test data, added a few more clusters, and divided it into 2 bins. And Sydney Vac in Australia looked at just the youngest, like 200 million years. And now what we see is a slightly different story. So now what we see is the very, very youngest stars don't have a lot of hot sub-Neptunes. They're consistent with the field rate, actually. Over some amount of time, between the middle-aged test stars and the middle-aged K2 stars, we see heaps of hot sub-Neptunes. And then out of the field stars, we see hardly any hot sub-Neptunes again, right? Now, when I started this project, I was looking for migration. I wanted to know when the hot sub-Neptunes got there. Because one of the ideas is that they don't form there, right? They form further out and they migrate in, as the cartoon showed earlier with when the protoplanetary disk is there. So I was actually hoping to measure a lower rate of hot sub-Neptunes than I got. So this is a lesson for the students in the audience. When I measured this, I sat on it for like a year. Because I was like, oh, that's so high. Why is that so high? And then Rachel published this result, and I was like, wait. It's a completely different data set from a completely different telescope, which says the same thing, which is that hot sub-Neptunes are very common around young stars. So now maybe the picture, there's a lot of caveats here, maybe the picture is that migration is happening over the first billion years, in which case it's not disk-driven migration, right? Because it's, the disk is gone by now. So some kind of migration is happening that's not disk-driven between 10 million years and 500 million years. And then mass loss happens. I don't love it. I really don't love it, guys. Young stars are really difficult to find planets around. These error bars are all over the place, right? You can see that. So I think we don't know yet the exact timeline of what's happening with hot sub-Neptunes, but there's really tantalizing evidence that multiple things are happening, right? And this is why I'm not coming with answers, I'm coming with questions. What's happening? Why do we go from 25% to 100% to 25%? Inner planets, man, they're tough. So this is, we'll come back to this animation, which was from Rachel's press release from those 2 green points in the previous plot. So an idea is that the planetary systems, we have migration in over the first hundreds of millions of years. We have mass loss happening as well. We have planets actually, getting eaten by the star, which is something that happens if you get too close, that we see evidence of, and that you end up with this snapshot today, which is a result of many processes all happening over different timescales. So it's messy. I don't love it, but it's clearly a multivariate sort of thing that's happening. And the one plot I'll add, this is from Saeed this year. Yeah, there we go. Saeed this year. Over that 3 to 9 gigayear, that K2 point, I just showed 1 point for K2. But this was, Miriam looked at the Kepler data over that time. And if you look at the isochrone, if you get isochrone ages for all those stars, you actually see hints of a continuing decline in planet occurrence rates over that, field star age, 3 to 9 gigayears, right? You're still seeing maybe a decline. So whatever's happening, I also want to stress that it's an ongoing process, right? Like if there's some dynamical thing or whatever, it's still happening, out here. It didn't just stop. Okay, let's move on to metallicity. Okay, so this is one of the oldest demographics results in exoplanets, which is that more metal-rich stars, this is solar metallicity at 0, more metal-rich stars make more giant planets, hot Jupiters really. Make more giant planets. So this is an old result, but a classic. This is the updated version from Kepler, from Eric's paper from a few years ago, showing, you see the same trend with the Jupiters of this shape, and showing that as you go to smaller and smaller planets, this metallicity correlation is still there, but it gets weaker, right? For the smallest planets, the super Earths, this is 1 to 10 days, so these are short period. For the super Earths, there's still a trend, but it's quite weak. Now, planet formation theories have predicted in various forms that there is some metallicity cutoff, below which you can't make planets anymore. There's just not enough heavy material in the disk to nucleate and form cores and start making planets. But unfortunately, those predictions were all past the left-hand sides of these plots, right? So this was what we could do with the radial velocity data and then Kepler. But the predictions were all in a different part of space. Now, I mentioned TESS looks at the whole sky. So this was a project led by Kirsten Bowley, who's now a Carnegie postdoc when she was a grad student with me. And what we did was take the 100,000 most metal-poor stars that TESS looked at that had spectroscopic metallicity, so we knew they were metal-poor, and we looked for super-Earths. We looked for planets in this smaller spin. Now, if you took the Kepler and K2 trend and continued it, she should have found, thank you, 68 planets, 68 super-Earths. And she found zero super-Earths past this, which actually puts a very, very stringent, like 5 sigma upper limit on excluding this continuing. This Kepler and K2 trend does not continue past minus 0.5. It plummets. There is some cliff. And this is really useful input, as I said, into those planet formation theories. If your planet formation theory is still working hard at -1, then it's probably needs some fine-tuning, because at -1, there's no planets anymore. We already know there's no Jupiters, and now we know there's no super-Earths either. So this is a really strong result. Let's talk about the galactic distribution of small planets, of short-period planets. So what we have is a cartoon of a cross-section of the Milky Way galaxy. There's the bulge at the center. We have a thin disk and then a thick disk. And these are all the stars that K2 looked at. So remember I said K2 did this ecliptic plane survey, did all these pointings around the ecliptic. The red points are M dwarfs and the black points are FGK stars. And this is interesting because look at the different populations that we probed with K2. We did thin disk stars and we did thick disk stars. And what did we find? We found that for these short period super-Earths and sub-Neptunes, there's actually a quite strong dependence on the number of small short period planets per star with the galactic scale height. The higher you get above the galactic plane, the fewer short period small planets you have. Now, because we just talked about metallicity, and you already know there's a dependence on metallicity, I want to point out, we know that there's a metallicity dependence for scale height, right? Like as you get higher above the galactic plane, you see, thank you, you see fewer metal-rich stars. But this is what that looks like, right? If the scale height, if you just took our local metallicity scaling relation, this is what you would see. So what we see is a much stronger impact than that. And this is a question for the theorists in the audience. So basically, we just threw this one out. We're like, what's happening? Is it something to do with what the galaxy was like 8 billion years ago? Is it something to do with dynamical history, radiation history? What's happening to these systems? And I'll say there was a recent paper by Sarah Ballard who examined this in some detail, and what she found was you couldn't just have a model that had a simple slope with time, right? The highest stars above the galactic plane are the oldest stars. And she found that you couldn't just have something be a straight function of age. This is what that looked like, and it wasn't a good fit. Instead, you had to have some kind of step function a few billion years ago where suddenly planet formation got better. They started making more planets, and then you could fit this slope that John was seeing. Okay, and the last one I'll talk about, this is the last one, Eric, is the stellar mass distribution of planets. Okay, so one of the interesting results from Kepler was that small, short-period planets got more numerous as you went to smaller stars, right? As you went to smaller and smaller stars, you got more and more small, short-period planets, which is a little counterintuitive, right? Because the stars are smaller, there's less material in the protoplanetary disk, so you might think that they would make fewer planets. But what we saw is that you saw many more planets. And this is a new result from Kevin Hardigree-Ullman, which is going to be submitted soon, showing that, you know, we see this increase for M dwarfs, for small planets. These are hot sub-Neptunes again. This whole talk I could have said, what's the deal with hot sub-Neptunes? But you guys are too young for Seinfeld, so I didn't. You see this increase. But we know it has to turn over at some point. Otherwise, brown dwarfs would have scads of super-Earths around them, and sub-Neptunes, right? And we don't see that. And at some point, you don't have enough material. And this is indeed what we find with K2, which has 10 times as many M dwarfs as Kepler, is you see this turnover in the sub-Neptunes. You don't see it in the super-Earths yet. You don't see a turnover in the super-Earths yet. And this is a population synthesis model that just came out this year from Pan and collaborators, showing for the super-Earths, they expect a turnover in the super-Earths. For them, super Earths went all the way up to 10 Earth masses, so sub-Neptunes is kind of in that bin. So they expect a turnover, and it's almost exactly the same place, but we don't see it for super Earths. All right. I'll get to the conclusions because I'm in my last minute. Okay, so I promised you questions, not answers. We have, from Kepler and K2 and TESS and radial velocity, a lot of really interesting correlations that we found. Correlations with planet orbital period, with planet size, with planet stellar metallicity, with planet galactic scale height, with planet stellar mass. There's all of these really interesting things that we found. Now, the hard part for everyone here is how do you map those to the mechanisms that create them? How do you take this snapshot, this like little tiny piece of the puzzle, and step back and abstract that into a global physics model that explains planet formation and disk evolution? And that's the challenge I leave you guys with. Thank you so much.
Okay, so again, please, if you have a question, and I'm sure there are many, please go to the mic on either side. And if the mic is difficult to get to, just wave your hand and I will come to you with the mic. So I will actually start with the first question.
Sure.
So Jessie, so you mentioned photoevaporation versus the core power mass loss.
Yes.
But I mean, it's entirely conceivable that these operate simultaneously, right? They're not mutually exclusive. And
Yeah. So
James
actually,
Owen wrote a paper.
Yeah. So the week that I submitted the paper, so I had this hypothesis test: where's this point going to lie? And I knew that photoevaporation had made this one prediction, that core-powered mass loss had made this other prediction. And I looked at the K2 data and I was like, yes, it agrees with one. So we submitted the paper, and that week, the two people who wrote the original like photoevaporation and core-powered mass loss theories got together and wrote a paper about how it's both, and that both happen at the same time. And I was like, all right, okay. So, you know, when I was describing core-powered mass loss, I was trying to also capture the fact that photoevaporation is happening to the part of the atmosphere that the inner residual heat is pushing up. So yes, they're both happening. The question is just like, when are they happening and which one is driving? And can we understand when and why from the underlying stellar properties, planet properties, etc.? So they're probably both happening. But this is always the way with any time we're testing theories, right? Like, disk migration and secular migration are both happening. It's just which one and when and why.
Jack?
Can you say something about, among these sub-Neptunes, you said something about constant density for low-mass stars. There's a peak suggesting water worlds, or constant equivalent density, uncompressed density, if you assume, versus the ones with hydrogen and helium atmospheres that have to be hydrogen and helium as functions of stellar mass, et cetera, et cetera.
So yeah, you can see once you get above 10 Earth masses, you deviate from both those lines because you do start accreting more hydrogen and helium. So I think this plot was super exciting when it first came out. And that's the problem is we haven't been able to reproduce it for any other set of stars. So it would be really lovely to see if this held up for FG and K stars, for solar type stars. But so far it hasn't. And yes, you can see where hydrogen and helium come into play. Sorry, I don't know if there's more to the question, but this is it. Yes, you can see where it starts to go. Yes, exactly. This is, you know, you could have chosen other types of compositions, but these are perfectly natural to choose, and they lie right there. It's kind of cool.
Actually, let me just start. Please introduce yourself when you ask a question.
Sure. Hi, Jessie. Laura Schaefer. Going back to the photoevaporation versus core-powered mass loss, there is probably a timescale difference for FG-type stars versus M-type stars.
So
have we seen any of that?
I tried to capture for each point which exact subset of stars it was for, to make it clear that these aren't all exactly apples to apples. But this is as close as we can get with the young star samples that we have. So they're not exactly the same, and yes, there are probably timescale differences. But if you take the M dwarfs out, that sample isn't big enough on its own. Look at the size of these error bars. They're like 50% error bars. If you try to slice this in any other way, you can't get anything interesting. So you kind of have to, but that's why you end up with this really very frustrating picture of like something is happening, but we don't know when, what or why or where. Yes.
Okay, thanks.
Hey, John Monnier, University of Michigan.
Hi.
I was wondering if you could expand a little in terms of going to planet properties to going to higher mass stars.
Oh, actually, Stephen Jackalone is going to talk about that later this week. So if you look at the, this one here. Yes, so actually out here we have A stars, and Stephen's going to talk about that, so I don't want to steal his thunder, but he has an interesting result. So this continues to go down, and Stephen will talk about it.
Artem Agishin from UC Santa Cruz. Thank you for the wonderful talk. So you mentioned we don't see the cutoff for super Earths yet. I was wondering if there are theoretical predictions, and since you said you're an observer, I'm actually even more interested in knowing whether we will be able to see it at the cutoff.
Oh yeah, so it could be that the cutoff is further down. So the prediction from this population synthesis, this pebble-driven population synthesis, so half a solar mass for this warm super Earth's box is, let me go back to here, half a solar mass for the warm super Earths is actually at about 3750 Kelvin, which is actually exactly where this is. This is actually 3757 or something crazy. So for the sub-Neptunes, the theory is doing right, but when you break it up into super Earths, we don't see it. And so I just found this paper last week when I was trying to put this talk together. So I'm really curious to go and chat to them now and be like, can you divide this up at all? Because you can see the data so these are, the open squares are radial velocity and the closed squares are transit results. You can see that the data don't actually match that turn down, right? You can see that that seems to flatten, which is actually what our data are also showing. So at the moment, the theory doesn't seem to have a prediction that works. The theory predicts a cutoff at 3750, and we don't have one. In terms of whether we're going to see it, so K2 might have been our best shot because it did look at 30,000 M dwarfs with Kepler-like precision, not exactly Kepler precision. TESS, because it's much smaller telescopes at 10 centimeters instead of a meter, these really cool M dwarfs are starting to be too faint, right, to do them in numbers, in the numbers that you would need to do this. And everybody hates a really cool M star. They're so faint, and they're also active, and it's just a pain. So whether or not we're going to do it for warm super Earths, I was about to start talking about Roman, but no, it's not going to do warm super Earths. I don't know if there's a better data set coming up for warm super Earths specifically. So I don't know if we'll see it. Again, I have to assume it turns over at some point, right? It can't keep going forever. But we don't have a good prediction for where, and we don't have a good data set for testing it right now.
Thank you.
Bennett Skinner, McMaster University. You talked about this turnover of the sub-Neptune occurrence rate with age.
Yep.
And you also talked about how a few giga-years ago there might have been a sudden increase in planet formation efficiency as kind of a separate argument. Could these two facts be related?
Yes. So this is actually really interesting. All of my thinking about planet formation with age is that these systems will evolve to become these systems, right? That what we're looking at is these systems 5 billion years ago. But that is in complete absence of the galaxy having changed in the last 5 billion years, or 6 billion years, or 9 billion years, or 10 billion years, right? So not everybody is married to a galaxy formation theorist, but some of us are. So when I was like excitedly telling my husband about this result and being like, look, we can see that it's still high. And he's like, well, but the galaxy is different. And I'm like, what? And he's like, yeah, well, 7 billion years ago was the peak of star formation in our galaxy, and the radiation environment was different, and the dynamical environment was different, and stars were born in more clustered environments and more radiant. And I'm just like, what? What's happening? So there's a whole layer on top of this, which is that the galaxy is changing. So you can't really separate those two things happening, which is that these might not be. In 5 billion years, these systems might not look like these systems because they were born in a different time in a different behaving galaxy. So it's a very good point. And we truly don't know because what we're working with is snapshots. And snapshots, what we want is a movie, but what we get is snapshots. And it's hard to work out if multiple different things are happening at the same time, which one was the one that happened.
Thank you.
No worries. I just made it much more complicated, I'm sorry.
Hi, Jessie. Jiwang from the Ohio State University. I want to ask you a question about the metallicity dependence.
Yeah.
So I think it's very compelling that, actually it's a galactic height.
Oh, this one? Yeah.
Yeah. It's very compelling that you show that even teasing out the metallicity effect, you still see the impact of the galactic height. But the dependence of metallicity has uncertainty there, right? So I would like to see, what relationship of planet.
Like how wide this is?
Yes, yes.
Okay. Yeah. I mean, all I can do is show you the width of this one, which is not very wide, right? For super Earths and sub-Neptunes, these are quite, good fits. So I would assume, if I had to do it, that this one, that this is not thick enough to capture this,
right?
And have it just be within the envelope of uncertainty of the metallicity.
And what is I forgot, but did you speculate what is the cost for this dropped occurrence rate versus galactic height?
Yeah, so I speculated, but I don't know the answer. So one of them is this age dependence, that these stars are much older and have had more dynamical interactions. And, if you look at it from the galaxy formation theory point of view, we're born in much more clustered, dynamically unstable environments. So these might have had planets get stripped, or planets interacted with each other such that they get pushed into the star so they don't exist anymore. Right? They might have formed and been stripped, or they might not have formed because of some truncation of the protoplanetary disk in these more clustered, more radiative environments. It's something to do with age. That's all I can say.
Yeah, just to add another piece of galactic archaeology information there. There could be young stellar population at the highest galactic height. So.
Oh yeah, this is, it's not linear that height and age are one-to-one for sure. So it's a question, not an answer.
All right. Thank you.
No worries.
Jack Lissauer, NASA Ames. You showed a plot of the planet evolution timescales. That was a logarithmic plot in time, suggesting that most of the processes would happen within the first 2 billion years or so. Has the galaxy changed much in the past 2 billion years? Or if we had enough data comparing 2 billion years, the most recent 2 billion years, could you answer your question?
Yes. So given that the processes that happen in the galaxy are similarly logarithmic to the processes that happen in a given planetary system, no, we don't think the galaxy has changed a lot in 2 billion years, right? So when I'm talking about galaxy changing, I'm talking about 7 billion years or 10 billion years, right? Like when interesting things happen. In the last 5 billion years, it's been pretty chill, according to my husband. So yeah, in the last 2 billion years. So if we could isolate the effects of these young systems that we see over here, if we could just roll these forward in time, right? If we could roll these forward in time, the galaxy, we don't think will change much in the next 5 billion years, right? It's done with a lot of its big things. Actually, in 5 billion years, it will eventually collide with Andromeda, and that'll stir up a whole new generation of stars and dynamics. And so 10 billion years from now, this planet population will look completely different because we collided with Andromeda and a bunch of interesting things happened. So yes, I think the last 2 billion years, quiet. The next 2 billion years, quiet. 5 billion years from now, stuff happens.
Lee Hartman, Michigan. Sorry, what's the difference between, on the very left, the green and the red dots?
Oh, that's just two different analyses of the same data. They're both test data. Sydney's goes to 200 million years, and Rachel's goes to 100 million years. But it's all test clustered data.
And are those the same mass range?
Yes, so they're all hot sub-Neptunes. In terms of stars, yes, they're FGK stars with TESS. It's the same stellar sample and the same planet sample. I actually think Rachel's goes up to 8 Earth radii and Sydney's might go up to 6 Earth radii. There's some slight difference in that upper envelope, but that's well past, if you look at the distribution, I think, it's well past where the numbers are really making a big difference to the bin. But they had different upper limits on their radius bins, it's true. But they're not where I would worry about it changing the answer.
Jesse, could you go back to the plot of the age versus the fractional occurrence again? So this will be your keystone plot of your keystone talk.
What's happening?
Could you talk to us about the error bars?
Yes.
You are one of the world expert on error bars and occurrence rates. And so
Yes.
we're all adults in the room. We can talk about the error bars.
Yes.
Can you say something about whether this is just simply number statistics that were limited? Are there systematics that lurk here? What worries you about these error bars?
Yeah, so as an example, these K2 data are based on 10 planets, right? So the square root of 10 is 3. So with 10 planets, you're only ever 3 sigma away from 0. Right? So this is partly, all of these, the dominant error is small number statistics. All of them, the dominant error is small number statistics. This bar in here is basically how, when you do occurrence rates, often you're fitting power laws, right? And this bar here is basically capturing 2 different power law fits. So that's another source of big uncertainty, is where you anchor your power laws, right? Because you have so much more information at short periods than at intermediate periods or long periods, when you're fitting a power law, exactly where you choose your short period cutoff, it's like the tail wagging the dog, right? Like it changes your answer a lot, because so much of your statistical power is at short periods. So this bar here is to try and capture the uncertainty in the power law that we chose. So the thin lines are the statistical uncertainty from small number statistics, and the thick bar is from the model we chose, the uncertainty that introduces. So you can see, you know, the thin bars are longer, but they're not 10 times longer, they're 3 times longer, right? So there's a significant contribution from model choice here, which I was trying to capture in this point. And you can assume that those are also true here. Now the K2 point, this has got like 400 planets in it, right? That's why this error bar is inside that box. So young stars, there's just not as many, and they're noisier, so it's much harder to find planets.
Okay, I think we are out of time now, so let's give Jessie another great thank you for this excellent talk.